Hello, pre-calc students. This is Mr. Beck. What I'm going to do today is I'm going to continue off with the notes of where we stopped last time in class. I'm sorry I'm not able to be in class today for my Gold Caramel cohort, um, but it is what it is. So what I'm going to do today, as I said, is I'm going to talk about the rest of 4.5, 4.6. We're going to blend all the information together. When I do this, the first thing I do want to take time to note is Descartes' rule of signs. It's not something I'm going to be testing, but it's going to be very, very beneficial, and I'll kind of show you why it's beneficial. The idea behind this is we want to see how many positive and how many negative zeros we have in the function. So what we do is we check to see the change in the signs of all of our non-zero coefficients of f of x. And we use that to determine how many positive solutions we have. For instance, if I take a look at this level 2 problem A, if I look, this is a positive, 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 positive. There are no changes in signs there. And because there are no changes in signs, that means that there are going to be 0, so no changes. Therefore, there are 0 positive solutions to this. Going back, what we could do is we could also check what is f of negative x. If we look at f of negative x, you'll see that I can do that right here. I'm going to erase all this information just because I probably won't erase this, but when I do this, I have negative 2x cubed plus 4x squared minus 18x plus 36. So when I do this, if you notice, I end up having a total of 2 changes of signs. We go from negative to positive here and then positive to negative here. I lied. We have 3. So we have 3 changes in signs. What this means is we could have 3 negative zeros. Now, we're not guaranteed 3 negative zeros. We're guaranteed that we have 3 negative zeros, or an odd number of these, we could have 1 negative zero. And what would end up happening to the other 2 zeros is that we have 2 complex zeros, which is in fact the case, because if you look at what this problem is, this problem says that we do have some complex zeros. And the reason why we drop down by 2, we say either 3 negative zeros or 1 negative zero and 2 complex zeros, has to do with the fact that complex zeros will work in pairs. That's our conjugate pairs theorem. Very, very important thing. If r equals a plus bi is a 0, then it's a conjugate r minus bi, or r equals a minus bi is also a 0. So once again, that's just a brief overview of what Descartes' rule of signs says. Therefore, I'm not going to be testing it. It's a very helpful tool for us as we go through some of the problems if we're kind of stuck saying, hey, what zeros do we have and why? So let's go ahead and begin the level 2 problem. Our goal with this level 2 problem is to find the remaining zeros. Now, this is where I'm going to use the conjugate pairs theorem to say, okay, if 3i is a 0, then so that would be 0 plus 3i. If that's a 0, then 0 minus 3i is also a 0. So I now know 2 zeros. Well, how do I find the third 0? Well, to find the third 0, I have a couple different possibilities of what I could do. We can use synthetic division just like we did before. Now, this is going to be kind of like the hardest one to do, only because there's a lot of computation involved, and you'll see what I mean when I get into it. So 2, 4, 18, 36. So 2 times 3i is 6i. Now, when we add those, we get 4 plus 6i. Now, 4 plus 6i, when we multiply it by 3i, will give us 12i, and then plus 18i squared. Now, if you remember, I squared is equivalent to negative 1, and because I squared is equivalent to negative 1, it really says that's 12i minus 18. So when I add those together, I get 12i. 12i times 3i gives us 36i squared, which once again, that becomes negative 36, giving us 0. So what we just identified was, 3i was a 0. We knew that because we were told that in the problem, but we just confirmed that. So from here, if we know that 3i is a 0, we're going to take that reduced function, that reduced polynomial function, and we're going to check negative 3i. So 2 times negative 3i is negative 6i. Add those together, we get 4. Multiply, we get negative 12i. Add those together, we get 0. What that means is my remaining factor is 2x plus 4. So, long story short, what we did was we took our function, which is f of x. I'm used to writing p of x now. So we took our function f of x and we broke it into x minus 3i from the first 0, x plus 3i from the second 0, and then 2x plus 4. Now, to answer the question, find the remaining zeros. The remaining zeros come from here, x equals negative 3i. And if we solve this one, we get x equals negative 2. Now, if you notice, we ended up with 2 complex zeros and 1 negative zeros, which is what Descartes' rule of sign said was a possibility. So, what's the other approach to doing this problem? Because I know a lot of people don't necessarily like doing that computation. You can't say that I'm always the biggest fan of it, but it works. I mean, really, it's the same kind of logic of what we used before. So our other possibility of what we could do is we could say, okay, I know that x plus or x minus 3i is a 0 because I was told that, or x minus, I know 3i is a 0, which means x minus 3i is a factor. So x plus 3i also has to be a factor, and that's because those two conjugates work together. Now, if I multiply those two together, I get x squared minus 3ix plus 3ix, and then minus 9i squared. Now that 9 minus 9i squared ends up being x squared plus 9. And what I could do is I could use x squared plus 9, and I could do some long division to say x squared plus 9 goes into 2x cubed plus 4x squared plus 18x plus 36. So x squared will go into 2x cubed 2x times. We subtract out 2x cubed plus 18x. We get 9x squared. Sorry, that's a 4x squared. There's a reason why handwriting is very, very important to have. Good handwriting, that is. Plus 36. Now, if how many times does x squared go into 4x squared? The answer is, of course, 4. And we get 0. So that's how we could get our remaining factor. Now, our overall goal is, what is that remaining factor? Because we knew what 2 of the zeros were pretty quickly. But then this allows us to find the other factor, and then at the end, our answer, which is going to be the remaining zeros. So next one is, let's find a polynomial function of degree 4 whose coefficients are real number and contains the zeros. Now, we have 3 listed zeros here. So what I know is I have a polynomial degree 3, but our goal is to find a polynomial degree 4. Well, in order for us to find a polynomial degree 4, this is where, once again, we're going to be using the conjugate pairs theorem to say if 2 minus I is a 0, we must have 2 plus I as a 0 so that we have real coefficients. So let me do this in blue just so I can have a different distinctive color. So what I could do is I can create my function f of x equals, let's go ahead and just list the zeros as factors, x minus 3, x minus 2, x minus 2 minus I, and then the hidden one, x minus 2 plus I. Now, when I do a multiplication problem like this, what I like to do is I like to multiply these two together first, and then honestly, it's very, very beneficial to multiply our 2 complex zeros together as well. Let's do that one first because that's kind of the more important one. Now, I could either do this, I mean, there's so many different possibilities how we can multiply through. Basically, it's the distribution process where the x has to be distributed to all 3, -2, et cetera, et cetera. Now, that ends up getting kind of messy, so I want to show you something that's a little bit nicer to work with. We could look at this as x minus 2. This is x minus 2 plus I. If we go ahead and distributed that, and this is x minus 2 minus I, we could group it as x minus 2 plus I times x minus 2 minus I, and we could treat this as a difference of squares problem. So if we FOILed this, the outer and the inner are going to cancel out. When I say the outer and the inner, it's going to be x minus 2 times x minus 2, which ends up being x minus 2 squared. The outer and the inner, x minus 2i, and then negative x minus 2i, those cancel each other out. And then we end up with negative I squared. So these two multiplied give us x squared minus 4x plus 4. And then negative I squared is plus 1. Hence, x squared minus 4x plus 5. So those multiplied out give me x squared minus 4x plus 5. These two multiplied out give me x squared. Outer and the inner is minus 5x, and then plus 6, which that's going to carry down here. And now we're kind of stuck to say there's not really a simpler approach to multiplying these two together. We're just going to have to distribute the x squared. So x squared times x squared is x to the fourth. X squared times negative 4x is negative 4x cubed plus 5x squared. Now I do like to line my terms up, so that's minus 5x cubed. And what I'm doing here is I'm now distributing that negative 5, and that's what's going to go on this line right here. So negative 5x times negative 4x gives me a positive 20x squared. Negative 5x times positive 5 is negative 25x. And now distribute the 6. 6 times x squared. 6 times negative 4x. And 6 times 5. And grand total, x to the fourth minus 9x cubed plus 31x squared minus 49x plus 30. This is my polynomial with real coefficients of degree 4. Now, the rest of our goal today is to do kind of like what we did last time, but this time we have to know that we're going to have the possibility of having complex zeros. Now, just kind of as a recap of what I said in class, if we're given a zero or given a factor, we use synthetic division to make life simpler, or we could do kind of like what I did right here. If we have the complex zeros, we could use the conjugate pairs theorem to figure out what that overall factor is and then use long division for that. Sipping my coffee, I ignore them. So from here, if those don't work, then if you remember in class, I told you. So in class, I told you, hey, I like to check P of 0, P of 1, and P of negative 1. The reason why I like to do that is because either it's going to give me a nice 0, or it gives me an opportunity that I can see a change in sign so that I can use the intermediate value theorem. So does this always work? No. But it's something that's very easy to do, and then it maybe gives us something, or it gives us a direction of where we can go from here. Now suppose that doesn't work, then we also have the rational zeros theorem, which means that it's going to be factors of the last term over the factors of the first term, and then we can test some of those values. Descartes' rule signs, as I mentioned, it's not required, but it's very, very beneficial just to kind of get an idea of what the nature of all of our zeros are. And then really, GCF, factor by grouping. Pretty much all the different factoring skills we learned in Algebra 2, those are going to come back to help us. And the moment we can get it down to a quadratic, we can use that quadratic in order to, or that quadratic formula in order to find all of our zeros or be able to write those as factors. But the most important thing is fundamental theorem of algebra. The fundamental theorem of algebra, this is really more of the corollary. I know I kind of like jumped over that, but every complex polynomial degree n has at least one complex zero, and from those complex zeros, you could break it into n linear factors, and from those n linear factors, we get n zeros. That's kind of like the nuts and bolts of what the fundamental theorem of algebra does for us. And that's why it's fundamental, because it says, hey, we have a polynomial. How many zeros do we have, or how many solutions do we have to this equation? This is just a way for us to find it. So let's go ahead and start our process. So I want to solve the following in the complex number system. One of the very first things I like to do is check, can I factor this by grouping? The answer, surprisingly, is yes, but I haven't taught you how to do that. At the very end of today's notes, if you're interested, you can stick around and I could show you how I would factor that one by grouping. But as of now, we don't really know how to factor this one by grouping. Since we don't know that, is there a GCF? No, I don't see a GCF here. Since there's no GCF, not factored by grouping, what I'm going to do is I'm going to say, let's make this f of x. So what is f of 0? What is f of negative 1? And f of 1. My hope when I do this is I can either see a change in signs or I can find a 0. So f of 0 is negative 6. And by the way, once again, I'm looking at this as the function I'm testing values in. If I plug in 1, f of 1, and put all that together, I will end up with negative 16. So it looks like I'm moving away from the x-axis. If I plug in negative 1, I get negative 24, which also means I'm moving away from the x-axis. So as a quick graphical idea of what's going on, I know that f of 0 is negative 6, f of negative 1 is negative 24, and f of 0, or f of 1 is negative 16. So what's happening is our graph is doing some kind of curvature down there. And the fact that we have curvature down there means that we have complex zeros that are going to result from this, not real zeros. Now, which side should I check? I would naturally check on the positive side just because this is a little bit smaller. Does that mean it's going to work? No, it doesn't, but it's still a reasonable guess. And more importantly, this is where Descartes' rule signs actually could help us. Again, not something tested, but I do want to stress the importance of it. If I plug in negative x, or if I plug in x, how many changes of signs do I have? You'll see one change of signs from positive to negative, then negative to positive, then positive to negative. This means I have 3 positive possibilities out of 4. And if I have 3 positive, that would be 1 negative. Or it could be 1 positive, 3 negative, to account for all of my complex zeros. Or really, I probably shouldn't even generalize too much like that. So it'd be 3 positive or 1 positive. Now, if I plugged in negative x, I would get negative, this is a positive 3x to the 4th still, minus 3x cubed, minus 17x squared, minus x minus 6. I only see 1 change in signs, so at most there's going to be 1 negative 0. So either I'm going to have 3 positive, and I guess it would be 1 negative. I would have 1 positive, I could have 3 negative, and then no complex, because I'm accounting for all my zeros by the fundamental theorem of algebra. Or I could have 1 positive, 1 negative, and 2 complex. Now, since I kind of hinted at, we have some curvature below the x-axis, that means that we're going to have some complex solutions. So this is going to be our natural guess of what's going to happen. And that's where I said Descartes' rule signs is a very beneficial tool for us. Not something that I'm going to test, but it's a very beneficial tool for us. So if I have 1 positive, 1 negative, and 2 complex, those complex ones are going to be pretty hard to find. So we're going to have to go with either one of the positives and one of the negatives. So what should we do? Let's just check 2. Now, if we plug in 2, plugging in 2 is not always going to be easy to think through sometimes. So let's just do it synthetically. So 3, 3, negative 17, 1, negative 6, 3. 3 times 2 is 6. Add those together, 9. 9 times 2 is 18. Add those together to get 1. 1 times 2 is 2. Add those times 2. We get 0. So we actually found one of our zeros. Now, I do like to take the opportunity to say, okay, now that I found one of those zeros, let's go ahead and factor this. This is x minus 2 times 3x cubed plus 9x squared plus x plus 3. That equals 0. That's what I'm trying to find. So now I can work with this. And if you notice, I do have some factor by grouping that occurs here. The factor by grouping, I notice my factor by grouping by the pattern or by the ratio of these terms. 3 to 9 is the same ratio as 1 to 3. So if I take my x minus 2, factor out the 3x squared, I'm left with x plus 3. Factor out 1, left with x plus 3. Then it gives me x minus 2, factor out the x plus 3, and I'm left with 3x squared plus 1. So now I can solve x equals 2. From here, x equals negative 3. From here, I will have x squared is negative 1/3. So x would equal plus or minus square root of negative 1/3, which if we rationalize by multiplying by the square root of 3 over 3, square root of 3, we will get I square root of 3 over 3, plus or minus. So we have now accounted for all of our different solutions. We have all 4. And if you notice, 1 positive, 1 negative, 2 complex solutions. Looking over here, suddenly this is starting to look more and more complicated. Now, with this being more and more complicated, is there a GCF that I could take out of this? And the answer is no. Some more coffee. Now, second thing, is this a factor by grouping? Once again, this problem actually is factorable by grouping. I haven't taught you how to do that, which at the very end, if you notice, that would be a great place to start. So if you want to tune in and see how to do that, that would be great. But since we're not officially doing that, then let's say, okay, well, what's next? So let's go ahead and say, once again, I'm going to look at this as f of x. So what's f of 0, what's f of 1, and what's f of negative 1? So f of 0 is going to be negative 18. And for those of you who are like, there's no function f, this is the function f I'm kind of looking at. What's f of 1? If I plug in f of 1, I get 3 plus 5, which is 8. 8 plus 25 is 33. 33 plus 45 is 78. 78 minus 18 is 60. Now, what does that mean? This is a great place to begin because what we could say is we know that there is going to be a rational 0 in between. Hopefully, you're going to be able to find it. So if there's a rational 0 in between, what could that rational 0 be? Well, the rational zeros, if you remember by the rational 0 theorem, rational 0 theorem says it'll be the factors of 18 over the factors of 3. Factors of 18 are going to be plus or minus 1, 2, 3, 6, 18. And then don't forget, we have to take those over the factors of 3, which are 1 and 3. So it'd be 1/3, 2/3, 3/3, 6/3, and 18/3 are all redundant. So I have a rational 0 that's going to be between 0 and 1. And it's either going to be a positive 1/3 or a positive 2/3. So the question I have is, which one does it look like it's going to be? Is it 1/3 or 2/3? As I look and say, the 0, is it going to be closer to negative 18 or closer to 60? General thought is I think it's going to be closer to 0, so I'm going to check 1/3. That logical reasoning is such a key aspect to how we approach these problems. So 1/3, 3, 5, 25, 45, and negative 18. So 3 times 1/3 is 1, 6 times 1/3 is 2, 27 times 1/3 is 9. Add those together to be 54 times 1/3 is 18. So I ended up finding my 0 and I kind of logicked it out. And that's what I'm hoping you guys do as well. Now, where do we go from here? Now that I used my 0 of 1/3, I will say this turns it into x minus 1/3 times 3x cubed plus 6x squared plus 27x plus 54. And that has to be greater than 0. Now, if you notice, there is a 3 that is part of each one of those. And this is x minus 1/3, so it's natural to factor out the 3 and then use that factor out the 3 and multiply the other factor by 3 to say 3x minus 1/3 times, or sorry, 3x minus 1. I was doing that a little too quickly. 3x minus 1 times x cubed plus 2x squared plus 9x plus 27. From here, if you could see, we now can factor by grouping. We could take an x squared out. When we take an x squared out, we're left with x plus 3. We could take a 9 out. We're left with x plus 3. So when we factor out our x plus 3, 3x minus 1, x plus 3, we're left with x squared plus 9. Now, I sort of ignored the overall goal of the problem. The overall goal of the problem is to figure out where this is greater than 0. So if you remember when we did our inequalities in 4.4, we have to list our real zeros. Our real zeros are negative 3 and positive 1/3. Our complex zeros, we don't have to list here because they don't cross the x-axis. So this is where we check some signs. As we check some signs, all of these have a multiplicity of 1, so they should change signs. But if we plug in, say, 0, we actually did. If we plug in 0, we get a negative. If we plug in, say, 1, we're going to get we get a positive times a positive times a positive. If we plug in negative 4, we are going to get a negative times a positive, which is also positive. So to answer the question, it would be negative infinity to negative 3, and then from 1/3 to infinity. So there's some 4.4 review built into a lot of the problems that we're doing here. All right, next one. Write the following as a product of linear factors. So this problem is really the reverse of the problem that we did up here. So what's our goal? Our goal with this problem is, let's go ahead factor completely. So can we, or do we have any GCF that we could take out? And the answer is no. Can we factor this one by grouping? And I actually think this one could be factored by grouping as well. If you hint, 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 stay tuned at the end of the notes and I can show you what's going on there. But with that said, since we can't officially do it just yet, therefore, let's go ahead and check some values. F of 0, F of 1, F of -1. If you notice, once again, this is just kind of like a very nice pattern what we can do. So F of 0 is 20, F of 1, we plug in F of 1, we get 1 minus 8, which is -7. -7 plus 25 is 18. 18 minus 36 is -18. -18 plus 20 is 2. So it actually looks like we're approaching a 0 at this point. We could plug in -1. We will get 1 plus 8, which is 9. And then 9 plus 25 is 34. 34 plus 36, remember, multiplying by -1. 34 plus 36 is 70. 70 plus 20 is 90. So I really think I might want to try to avoid what's going on here on the negative side because it looks like it's moving further and further away from 0. It doesn't mean that it's not. It's just a little less likely in my opinion. So what I'm going to do here is let's check 2. And anything beyond 0, 1, or -1, I tend to do synthetically. You can directly plug it in if you're that good numerically, which I encourage, and I think that's great. So let's plug in 2. And again, the reason why I'm plugging in 2 is because it looks like we're approaching 0 here. So 1, 2, -6, -12, 13, 26, -10, -20, and I have 0. So yay, this is great. That means that in my quest to write this as a product of linear factors, which I'm going to write down here, I know that x minus 2 is one of the factors. Now it's at this point that I have to say, okay, what can I do? Or what should I do? Well, I don't see any factor by grouping here. I don't see any GCF. And when I say that, I'm really looking at this as 1x to the third minus 6x squared plus 13x minus 10. So that's what I'm looking at. So what do? Hey guys, I think we should just try again. So if there wasn't a 0 between 0 and 1 here, there's not going to be a 0 there again, just because if it's part of the reduced equation, it's going to be part of the original one as well. So what should we try? And this, everybody else say, is where a lot of students fail. They're like, hey, I used to, and 2 gave me a 0. Guess what? We probably want to check 2 again. The reason why is because it's still a possibility. If you think all of our factors of 10 are 1, 2, 5, and 10. So if we check those, or if we check 2 once, let's try it again just to see if it works. So 1 times 2 is 2, -4 times 2 is -8. Add those, positive 10. And then those add to be 0, which is great because now I know my second factor is also x minus 2. And I'm left with this quadratic x squared minus 4x plus 5. We could do a couple different things here. Number one, we could use the quadratic formula. If we use the quadratic formula, we get x equals -b plus or minus the square root of b squared minus 4ac all over 2a, which gives us 2 plus or minus, and that's a 16. I know the handwriting's bad. 2 plus or minus 2i over 2, which is 1 plus or minus I. So actually, I made a slight mistake on that one. That was supposed to be 4 plus or minus 2i, so that's 2 plus or minus I. So what that means is we would have x minus 2 plus I and x minus 2 minus I. Those are going to be my rational zeros. What I like to do, and I showed at least one class this last time, is there an easier way that I could think through this? And this is where I would like to split up that 5 into something a little bit more fun to work with. X squared minus 4x, I will say what completes a square, and what completes a square is a positive 4. And now we can say how is 5 split if positive 4 is what I'm looking for. I could split 5 into 4 plus 1. And the reason why I want to do that is this is x minus 2 squared plus 1, or x minus 2 squared minus a -1. Now when I do that, The reason why I have it written in this form is this is the difference of squares. So we factor into the square root of the first plus the square root of the second, and the square root of the first minus the square root of the second. X minus 2 plus the square root of the second, which is I, and then that's one factor. The other factor is x minus 2 minus I. And if you notice, that's really what we have down here if we remove the parentheses. So a lot of students go, wait a second, that was kind of weird. I'm not sure I got that. It does not matter to me how you get it. I think that this is a stronger mathematical approach, and it kind of uses the difference of squares to our benefit. However, a lot of students are like, I'm not sure, I'm not comfortable, and everybody, that's totally okay. You could solve by the quadratic formula and then put it down there. Then we get to our next problem. One of the things that I want to look at, and this is a perfect example of where Descartes' rule of signs kicks in. As I look at this equation, there are no changes of signs. Since there are no changes of signs, Descartes' rule says there are no positive zeros. Since there are no positive zeros, that's an indication for me, don't bother checking anything positive. And this is where, since I already started with Descartes' rule of signs, let's go ahead and say, what is f of negative x? F of negative x is x to the fourth minus 6x cubed plus 11x squared minus 12x plus 18. And when I look, I have 4 changes in signs. Those 4 changes in signs means I either have 4 negative zeros, I'll have 2 negative zeros and 2 complex, or I'll have 0 negative zeros and 4 complex. Now, do you think it's really a problem that I'm going to give you where I'll have 0 negative zeros and everything's complex and I'm going to make you have to do that on your own? The answer is no. So as a teacher, I would not do that to you. That's not going to be a possibility. So it's either going to be 4 negative zeros or 2 negative zeros and 2 complex. Everybody, guess what? Since this is working with complex, this is probably what's going to occur. And I say probably, there's no guarantee. Let's just go ahead and do it. So normally, there's no factor by grouping. Actually, there is, but we can't look at it as factor by grouping. Is there a GCF? The answer is no. So f of 0, f of 1, and f of negative 1. So f of 0 is 18. I didn't write that very well. F of negative 1. What is f of negative 1? It's going to be 1 minus 6, which is negative 5. Negative 5 plus 11 is 6. 6 minus 12 is negative 6. And then negative 6 plus 18 is 12. So it looks like we're starting to get closer and closer to the 0. I'm not even bothering to check that, mainly because Descartes' rule of signs says it's not going to be possibilities. If you really checked it, I believe you're going to get, I think it's 6, but anyway, it doesn't matter. Let's go ahead and now check negative 2. And again, remember, I'm checking only negative values because Descartes' rule of signs says there's not going to be any positive zeros. So this is definitely a situation where knowing Descartes' rule of signs helps. Is it required? No, of course not. So 1, negative 6, 11, negative 12, 18. 1 times negative 2, negative 8, times negative 2 is 16. Just want to make sure I'm doing this right. Yep. So, you know what? I knew something wasn't quite right because I'm plugging it into the wrong one. Let's plug it into the top one, shall we? All right, let's try that again. All right, 1 times negative 2, add those. 4 times negative 2 is negative 8. 3 times negative 2 is negative 6. 6 times negative 2 is negative 12, which gives me 6. Since that gives me 6, not quite what I'm looking for. Now, remember, just because it didn't give us what we were looking for doesn't mean we discard it. Let's put this information off to the side. If you notice, it appears that we're getting closer and closer to the x-axis. So the next natural one I should choose is probably negative 3. Now keep in mind, I do want to only choose factors of 18. And the reason why I want to choose factors of 18 is because, no, the rational zero theorem. So -3 is a factor of 18. So let's check that. So 1, 6, 11, 12, 18. 1 times -3, 3 times -3, 2 times -3, 6 times -3, and lo and behold, we found one. So as I'm looking for what are my factors, I know f of x is going to factor into the 0 that we found, which is x plus 3. Now I don't know what my remaining factors are. I still can find my remaining factors if we take a look. Hopefully you notice the factor by grouping in this problem. We could use that to our advantage. So this is now x cubed plus 3x squared plus 2x plus 6. We can factor out the x squared, we're left with x plus 3. We can factor out the 2, we're left with x plus 3. So factor out the x plus 3, and we're left with x squared plus 2. So our next factor is also x plus 3. Now, how do we take x squared plus 2 and we write that as a product of linear factors, which is what we're required to do, because x squared plus 2 is quadratic. This is where, once again, I'm going to be a little creative and say this is x squared minus -2. So the square root of the first is x. And then we'll take the square root of -2. The square root of -2 means we're going complex. So the square root of -2 is I times the square root of 2. So that would be x plus I squared root of 2 and x minus I squared root of 2. So those are remaining factors, x plus I squared root of 2 and x minus I squared root of 2. There's our product of linear factors. Now, let's take a look at this, and I think I might need to apologize in advance that I did not give you enough space for this, just because of all the different things that we're going to have to do with this. So, how do we approach this problem? Our goal is to graph this, so this is some practice with 4.2 and 4.3. So, with this practice of 4.2 and 4.3, in the form that we have here, one of the things that I can identify is f of 0 ends up just giving me -12 over -6, which is 2. So I do know the y-intercept of this graph, and that's what the standard form is going to give me. Now, as the standard form gives me that, then I mean, pretty much that's going to be the only major thing, because if we look at our degrees, just some 4.2, 4.3 view, the degree of the numerator is greater than the degree of the denominator, so there's going to be some long division that we're going to be doing here. So I hope we're prepared for that long division. At the same time, and the reason why we need to do the long division is to figure out what our slant asymptote is. So be prepared for that. But most importantly, I want to get this into a form of what are my factors, what are my 3 factors over my 2 factors. So if I can get it into that form, I can see where my vertical asymptotes are, and then I could also see where my zeros are. So let's get going with this. I'm going to start by factoring the denominator, because factoring the denominator is definitely a lot easier. X minus 3 times x plus 2. Now to factor the numerator, this is where we're going to use the skills of what we did in 4.5 and 4.6. X cubed plus 2x squared minus 11x minus 12. I look at this and say, all right, do I have any factor by grouping, or do I have a greatest common factor? And the answer is no to both of those. So then we're just going to have to check some values. We know all of our rational zeros are factors of 12 over factors of 1. Are we going to use that? I don't know, but let's go ahead and check. So from this polynomial, I'm going to call this P, just so we don't confuse it with F. So from this polynomial, P of 0 is -12. P of 1 is going to be 1 plus 2 is 3. 3 minus 11 is going to be -8. -8 minus 12 is -20. So to me, this kind of looks like we're moving away from the x-axis. So let's check -1. P of -1, that'd be -1 plus 2, which is 1. 1 plus 11 is 12. 12 minus 12 is 0. So that tells me that -1 is going to be a 0. That's a very happy thing, because I think that's the first time that we found a 0 just by plugging in 1 or -1. So 1, 2, -11, -12, 1, -1, 1, -1, -12, 12, 0. So I know that x plus 1 ends up being a factor, and then I have to work with x squared plus x minus 12 is the other factor. The other factor then will factor into x plus 4, x minus 3, and that completes my numerator. So x plus 4, x minus 3. Now some overall analysis of what's going on here. So now that I have my numerator factored completely, what I do see is that I do have a common factor of x minus 3. So we can rewrite this as x plus 1 times x plus 4 over x plus 2. But x is not allowed to equal 3. Now, if you remember, and there's some definite review built into what we're doing today, this means that we have a hole in the graph. So at x equals 3, we have a hole. And we can find that by saying, what's the limit as x approaches 3 of f of x? And I could use my reduced equation to do that. That would be 3 plus 1 times 3 plus 4. And unfortunately, handwriting's starting to get a little bit bad on that. 3 plus 1 is 4. 3 plus 4 is 7. And 3 plus 2 is 5. So 4 times 17 divided by 5 is going to be 5 3/5. So 5 3/5. So I have a hole at 3 comma 5 3/5. So 1, 2, 3, 4, 5 3/5. So we have a hole right about there. Okay. So that hole once again comes from the fact that x cannot equal 3. Now, let's go ahead and focus on this reduced equation again. I'm going to change colors just so you know where I'm at. So I'm focusing on this reduced equation. And that says my x-intercepts are at -1 and -4. And then my vertical asymptote is at x equals -2. So you can see I'm starting to frame the graph a little bit well. Now, the only thing that I have left to do, is I need to find my slant asymptote. So how do I find my slant asymptote? I can go back and do long division from the beginning, or since I have this in a reduced form, let's go ahead and do some long division with, or synthetic division even, with this reduced form. So let me do the synthetic division in a different color so you know what I'm doing here. Let's do some synthetic division. -2 goes into, I guess I do need to multiply those back out. X plus 1 times x plus 4. That's x squared plus 5x plus 4. 1, 5, 4. So 1, -2, 3. 3 times -2 is -6. So remainder is -2. So what I did here was I said I could also write f of x as x plus 3 plus -2 over x plus 2. And then one of the things is x is still not allowed to equal 3 because of the hole. So x is not allowed to equal 3 because of the hole. Now, honestly, this would have been a little easier to plug in to figure out where the hole is at this point, but that's okay. So that slant asymptote, y equals x plus 3. Slope is 1. So it's going to look like that. And then we can sketch our graph to fill in what's going on. So it's going to curve here. Remember to leave space for the hole. Approach the asymptote. And then over here. Now I realized I kind of jumped over how we did some of that graphing in terms of the signs. So just as a quick review of how we do that. -4 is a 0. -2 is an undefined. We have 1, which is a 0. Now, I'm not going to include 3 just because we know that it's a hole and it's positive. But if we do check signs and we plug in -5, we will get negative, positive, negative, positive. And those all change signs because of the multiplicity of 1. So, one last problem, guys. So now we have this. So x cubed plus x squared minus 7x minus 7. One of the things that I hope you noticed right from the beginning is that numerator is factorable by grouping. So this makes our life just a little bit easier, and I'm thankful for that. And our denominator is also factorable. So numerator, if I take out the x squared, I'm left with x plus 1. Take out the minus 7, I'm left with x plus 1. Denominator, x minus 2, x plus 1. So I think there's going to be a hole in this graph too. So this is x plus 1 times x squared minus 7 over x minus 2, x plus 1. And those x plus 1s are definitely going to reduce because they're the same. However, we need to maintain our domain. So this is x squared minus 7 over x minus 2 as long as x does not equal negative 1. Let's go ahead and find the hole. So what's the limit as x approaches negative 1 of f of x? And we'll get negative 1 squared minus 7. So 1 minus 7 is negative 6 over negative 3, which is 2. So we have a hole at negative 1 comma 2. Let's go ahead and plot that hole right now. X squared minus 7, we could factor it into linear factors. X plus the square root of 7, x minus the square root of 7. Is that required? Not really, but it just kind of like reinforces the idea of we could break this into the product of linear factors, use that theorem. So the square root of 7 is going to be 2 point something. Let's say right about here. Negative square root of 7 is negative 2 point something, so right about here. We do have a vertical asymptote from our denominator, x equals 2. Let me go ahead and plot that in. And looks like we're going to have to do some long division one more time, or synthetic division in this case. And again, I could do the long division from that form, or I could do the division from the reduced form. I would prefer to do it from the reduced form just because it's easier, and we can do it synthetically. So 2 goes into 1, 0, negative 7. That's 1, 1 times 2, 2, 2 times 2. So what that means is we could also write f of x as x plus 2 plus negative 3 over x minus 2. Don't forget, x is still not allowed to equal negative 1. So that means my slant asymptote is y equals x plus 2. So y equals x plus 2. Here's my slant asymptote. And then hopefully you can see what's going on. I guess I haven't found the y-intercept yet. Y-intercept, if I plug in 0, I will get 3.5, which would be right here. And this is where I hope that if we, or you could see the progression of what this graph is going to do, which will be, oops, not over there, right here. And if I did the number line test, I had square root of 7, negative square root of 7, that is. I'm not including negative 1. I will have 2, and I will have the square root of 7. So checking my values would be negative, positive, and therefore I have my graph. So hopefully this was beneficial for you because you got to see my entire thought process as I did every single problem. Good luck to you, and have a great day.